So chapters 3 and 4 both relate to the voltage and current equations for capacitors and inductors. From an energy perspective, what is different about inductors and capacitors when compared to resistors? Anyone? From an energy perspective. Resistors do not store energy. Capacitors and inductors can store energy. All three components can receive energy. However, resistors will dissipate this energy in the form of heat. Capacitors and inductors, well, anytime there's energy transfer, there's always loss of energy, or some fraction of the energy is lost as heat. Resistors dissipate all of it as heat. Capacitors and inductors can actually receive the energy, store it, and then release it back into the circuit at a later point in time, depending on circuit conditions. Okay. So again, they are energy storage devices. Capacitor, capacity to store energy. Okay. So both of these are energy storage devices. They're still passive. They're not active. Active means a power supply that can supply its own energy. Capacitors and inductors are passive components. They cannot supply energy of their own. They can only receive it, store it, and then release it back into the circuit. So again, both are still passive devices, but energy storage devices. Inductors can store the energy in a magnetic field. So inductors store energy in magnetic fields. Whereas capacitors store it in an electric field. More accurately, the electromagnetic field and electrostatic field. But we simply say magnetic field and electric field. The analogy I always like to use is a bucket of water. Okay. Think of the capacitor or an inductor as a bucket that you're filling with water. The water represents the energy. Okay. Depending on the size of the bucket and the flow of the water, the time taken to fill it up can be less or can be more. If the size of the bucket is large, it can store a large amount of water, meaning it can store a large amount of energy. Depending on the flow of water, whether it's slow or fast, the time taken can be slow or fast. The time taken can be less or more. Okay. So in chapters 3 and 4, we are going to find the voltage and the current for the energy or for the capacitor and the inductor at any given point in time. In chapter 3, we will talk about a little bit about the physics, not about the physics, but about the equations for voltage and current. And then in chapter 4, we'll look at the equations for voltage and current at a specific point in time. Now we talked about energy being received into these components and energy being delivered or discharged by these components into the circuit. That energy charging or discharging or receiving and delivering cannot take place in an instant. We cannot simply snap our fingers and expect it to happen in an instant, right? It takes a finite amount of time for the energy to be received by these components and then to be released back into the circuit. The time that it takes, again, for the energy to be transferred completely in both directions is dependent on the size of the capacitor and the circuit configuration. Okay, so in chapter 3, we'll simply look at the voltage and current equations and then power and energy. But in chapter 4, we will look at the equations during the energy transfer process. Again, the energy is not transferred from the source to the capacitor or an inductor in an instant. It takes a finite amount of time. So during this energy transfer phase, whether it's from the source to the component or from the component to the source, the voltage and the current keeps changing. And so in chapter 4, what we'll analyze is the value of the voltage or current at any point during the energy transfer phase. Make sense? All right. So let's look at, we'll start with the inductor first. As I stated, inductor stores energy in a magnetic field. Magnetism plays an integral role in almost every electronic device, electric circuit that we use today. Our generators, motors, transformers, television, radio, wireless charging, cell phones, satellite communications, pretty much anything to do with wireless is all based on electromagnetism. Okay. I'll add TV, radio, any sort of wireless communication, all employs the principles of electromagnetism. Now, research into electromagnetism took place over several centuries, but the known records go back just a couple of centuries. Okay. And as with anything in life, there could be multiple people working on the same topic all around the world at the exact same time, completely unrelated to each other. The person who releases the information first, who publishes the information first, becomes associated with it, becomes famous for it. And so in 1820s, there was a French physicist by the name of André Marie Ampère. He published a paper detailing his experiments with electromagnetism and his experiments with electric current, which later came to be known as Ampere's circuital law. Okay, and hence the name for current is named, the unit for current is named after him, Ampere. And then subsequent years after the publication of his experiments, we had several researchers who worked in electromagnetics, in the field of electromagnetics. Most prominent among them were Carl Gauss, James Maxwell, Michael Faraday, right? Unit for capacitance comes from farads, Faraday. Maxwell wrote out a set of equations, Maxwell's equations that are very famous. They are considered to be the foundation of electrical engineering or the field of electrical engineering. If you have an EE buddy, you can talk to them about Maxwell's equations, see how they scramble brains. Okay. Anyway, the point is research has been going on electromagnetism for like several centuries. We will not get to the device physics. We'll talk a little bit about the physics and the setup of the magnetic field, and then we'll stay on the engineering side of things, okay? Voltage and current specifically. So, if you have a wire or a conductor, it inherently has inductance, resistance, and capacitance. Okay. Any wire has certain amount of resistance, it has certain amount of inductance, and a certain amount of capacitance. It's an inherent property. So if you would take, for example, if you consider resistance and you take a 100-foot extension cable, a power cord, like the orange ones that we see, right? You plug it into a wall. If you expect 120 volts at the power outlet, you would expect to see 120 volts 100 feet away. The wire, if you measure the resistance of that long wire, it will have some resistance, few ohms at most, but it does not rise to the level of interference, meaning 120 volts, its job is to transfer 120 volts from one end to 100 feet away. The resistance of that wire does not rise to the level of interference. At most, that 120 volts may drop to 119 perhaps, but it does not interfere with the operation of our equipment. In the same way, that wire has inductance, it also has capacitance, but it does not rise to the level of interference. Okay, so any wire is capable of, not capable, it has inherent inductance, capacitance, and resistance. When current passes through a wire, it establishes magnetic flux lines. Those magnetic flux lines, comprised of photons, can be represented by the right-hand rule. The right-hand rule states, if you hold a wire in the palm of your hand and you bend your fingers with your thumb extended outward, If the thumb points in the direction of the current, then your fingers are pointing in the direction of the magnetic flux lines. Magnetic flux, again, is made up of nothing but photons, similar to our visible light, except that the frequency spectrum does not fall within the visible spectrum of human sight. So it's not visible to us. Anyway, so those magnetic flux lines comprise the magnetic field. Okay, the energy is stored in there. So again, the flux lines, spell check, is given by the right-hand rule. So to make sure the recording is not interfered with. Okay, still working. Now, this magnetic field is very weak. Okay, it does not rise to the level of interference. Depending on your application, it does, but most of the time it doesn't. Okay, as I said, if you take a 100-foot-long power cable or power extension cord, it'll work just fine. If you have an HDMI cable and you connect it to, let's say, your gaming console or your computer, and you send the signal 100 feet away to a projector or a television set, it will not work because the resistance and the inductance and the capacitance of that HDMI cable will rise to the level of interference. It will interfere with the signal reaching at the other end. So again, depends on the application, depends on what the value is. If you take that same cable, the point here is that the field is very weak. Okay, when a current passes through a conductor, it establishes a magnetic field, but that magnetic field is very weak. If you take that same wire, if you take that same conductor and you form a loop around it, all the magnetic flux lines get aligned. Again, remember, you have a current carrying conductor this way, your magnetic flux lines are going in this direction, and you wind it up in a loop, all of them are going inward, or you can say outward, depending on your perspective. But they all point towards the same direction, which is noted right here. Okay. If you look at from the other side, you can say they're all pointed outward. They come into that loop and go outward in that same direction. Again, the field is weak. If you now take and form multiple loops of that same current carrying conductor, that magnetic flux lines align. You of course have individual ones, right? All of them have individual ones, and we're only showing some of them. We're not showing all of them. But there's a larger line that goes through the center of that coil. And in this illustration, those flux lines, it's a closed oval or a closed circle. So there is no beginning or no end to those lines. But we say that they're entering from the right and exiting from the left. And they establish or they imitate the magnetic field of a permanent magnet. So it has a north and a south pole. Okay. So this magnetic field imitates a permanent magnet. But because the center of that coil is empty, it's just made up of air. Air does not have high permeability. Permeability of a material is the ease with which magnetic flux can be established through it. Air does not have, so this is an air core, if you will. It's just air. So some researcher somewhere discovered that if you insert a ferrous material through the center of that coil, you can strengthen the magnetic field. The magnetic field is now stronger because the permeability of that material is higher. It can establish a magnetic flux line with ease. And so this material can be iron, steel, which is nothing but iron, with a few additives, cobalt, etc. Inside the core, the magnetic field is now much stronger. And that is the working principle of an electromagnet. You take a large coil with a huge amount of current flowing through it, with a big core of iron material or ferrous material, it becomes a very strong electromagnet or a very strong magnet. Okay. And it can be used in place of a permanent magnet. Right? Permanent magnet. So the current flows through a coil of wire. Call it an inductor. It establishes a magnetic field. It stores the energy in that magnetic field. Symbol is given by simply a spiral coil, similar to a resistor. You would draw it either horizontally or vertically, depending on the circuit. I in electrical engineering is reserved for current. C is reserved for capacitor. And so we use L to note an inductor. It's an uppercase L. Lowercase l is for length. Uppercase L is for inductor. And the unit is, anyone? Unit for inductance? Henry. Named after an American physicist, Joseph Henry. I would like to say it's named after me, but I didn't discover it. H for Henry. Joseph Henry. So again, inductors are passive components. They can only store and release energy, which is associated with the magnetic field. Actually, you know what? Oh, as I said, it's a passive component. So it follows the passive sign convention or the passive reference configuration you saw in chapter 1 for resistors. What does passive sign convention mean? It cannot supply energy of its own. So it means that current always flows from high to low, plus to minus. So if you're given a voltage polarity, then the current will go from plus to minus. If you're given the current direction, then the point of entry is plus, point of exit is minus. It is indicated right here in illustration B. Okay. Capacitors, inductors, and resistors are all passive components. Okay, they're all passive components, so they follow the passive sign convention. Current always goes from high to low, or flows from high to low, plus to minus. If you're given voltage polarity, point of current goes from plus to minus. If you're given current direction, point of entry is always plus. Okay, point of entry is always plus. When current is for capacitor, we talk in terms of voltage as application of input. For inductor, we talk in terms of current. Okay, so when current is applied to an inductor, it goes from 0 to, let's just say, 1 amp. Okay, so it goes from 0 to 1 amp. It cannot change instantaneously. It takes some time for the energy to be transferred. Okay, it takes some time for the energy to be transferred. So between the values of 0 and 1 amp, the current is changing in value through the inductor. Does that make sense? So when the current is changing, a voltage will appear across the inductor. Once the current reaches its value, whether it's going from 0 to 1 or 1 to 0, once it reaches its final value, then the voltage does not change. The voltage goes to 0. Again, this is just a very short explanation. We'll look at the quantitative equations later. But again, important to note that the voltage will only appear across an inductor when the current value changes. If the current is constant, excuse me, then there is no voltage across that inductor. Okay. So 1 Henry of inductance is defined as the level of inductance that will cause 1 volt to appear across its terminals due to every change of current in the amount of 1 ampere per second. Okay, quite a mouthful, but don't get too bogged down in there. 1 Henry of inductance is or can cause 1 volt across its terminals for every 1 amp, for every change in current at the rate of 1 amp per second. If the current does not change, the voltage goes to 0. But again, that's separate. So 1 ampere per second change, 1 volt is 1 Henry. Real life inductors are much smaller. They're on the order of millihenry or microhenry. Very, very small. Very, very small. I just said about wires and cables that inherently, even when there is no current flowing through it, inherently has some inductance, right? That inductance is so small that we cannot even measure it. But sometimes it will rise to the level of interference. Okay, I'm going to end class here today. I will keep the Zoom meeting open and I'm available for a few minutes if anyone has any questions. Okay, otherwise I'll see you all on Wednesday.